Trust me, I would never lie to you. Well, I probably would, but that's beside the point. So, we're going to talk about some differentiation techniques. Different ways to take a derivative without using that big scary limit problem, which, if you did the homework yesterday, you realize can be a major pain in the buttocks. Okay. However, I'll show you some tricks today that will make things ridiculously simple. And for those of you that moved down from BC or maybe seen this in physics, you know what I'm talking about, and you'll realize that this is ridiculously easy. So, two screens of you should be able to, because we're going to cover a lot of stuff in this section today. Again, like I said, we're going to cut it short. So we'll talk about something called the constant rule. What happens when you take the derivative of a plain old number like 7? We'll talk about the power rule, which is going to rock your world and make your life a lot easier. Then we'll combine the constant rule with the power rule to the constant multiple rule. Then we'll go on to the second slide and talk about sum and differences. That's pretty easy. The derivative of a sum is the sum of the derivatives, and the difference of a derivative is the... No, I said that wrong. The sum of the derivative is the derivative of the sum. Notice no product and quotient up there. We get to that later. And of course, we need to talk about trig, which we'll save for later. And then we're going to do some physics with rates of change. So the derivative for us will be defined as 3 different things. You've had one already. It's the slope of the tangent line. The second one is a rate of change. And then the third one, you probably talked about in physics already, it's a velocity. Okay. So all that in this section. But we're going to stop after the sum and difference rules, so your head doesn't explode. Okay, so constant rule. Let's take a function like y equals 7. So before I click on the slide, what can you tell me about that function? It's a horizontal line. So what would the derivative of a horizontal line be? 0. Right? Because the derivative of a line is the slope of that line, and the derivative of, or the slope of any horizontal line would be 0. So anytime you take the derivative of a constant, you get 0, which is what that says. Okay. The derivative of c, a constant, is always equal to 0. Now, I have a couple different examples here, and it's not because you don't get it. I just want to show you some different forms. So for instance, if I had a function y equals 7, the way to represent the derivative would be dy dx, the derivative of y with respect to x. However, if I had f of x, then we would call that derivative f prime of x. Same thing, just a different way of representing it. If we go back to s of t, so maybe it's not x, maybe it's t. You know, when we start doing some physics there, where s of t is the position function, then its derivative would be s prime of t. And then lastly, why is the derivative of pi squared 0? It's a constant, correct. And the derivative of any constant is 0. That will trip up some of you. You know at some point in time I'm going to ask you for the derivative of pi or the derivative of e, and see how you handle that. Do you remember that it's a constant, or do you treat it like a variable? Okay, here we go, the power rule. Does anybody know the power rule yet? Any BC move downs? Well, yeah, okay, a couple of you got it. Okay, good. Explain it to me then. What does that mean in English?
So you like take the power, and then you move it to the front and multiply it by the variable to the power minus 1.
So, what's the derivative of x to the 8th?
8x to 7.
Beautiful. That's supposed to be a 7. Okay? It's that simple. You bring the exponent down in front, you reduce it by 1. So you'll notice in the notation there, in the calculus speak in the rectangle, if you're starting with x to the nth, then the derivative is n times x to the n minus 1. Bring the exponent down, reduce it by 1. And as it says, this is really important. You will do this ad nauseum. Do you know what ad nauseum means?
Yes.
What? It's Latin, which means until you puke. Okay? So that's why it flashes. All right, so that having been said, what's the derivative of x cubed, Michelle?
3x to the squared.
Perfect perfectly done. Any problems? Okay, let's ramp it up a little bit. What's the derivative of the cubic root of x, Kate?
Physics.
1/3 x. I don't know. Let me think. I'm so sorry.
You're getting tripped up on a subtraction problem?
Yeah. It's a third minus 1.
What's 1/3 minus 1?
Oh, -2/3.
Beautiful. Now I got a little fancies in my panties there because at some point you're not going to be allowed to use negative exponents. So you're going to have to get rid of those. However, today I would be ecstatic if you could get to just this, 1/3 x to the -2/3. Does everybody see where that came from? Cubic root of x is x to the 1/3 as it says in brackets, and then like she did, bring the power down, reduce by 1. And remember, you're reducing by 1, so you should be able to subtract 1 from just about anything. Elliot, your turn.
Okay. 1/2x. Nope.
Nope. You want to rewrite that first before you take the derivative? And what would that be if you rewrote it?
X to the -2.
I agree. Okay. So if this is the same thing as x to the -2, then what's the derivative?
Negative x. Oh, wait. No, -2x.
To the,
Negative first power.
what's -2 minus 1?
-3.
There you go. Okay. Rewrite that as x to the -2. Bring the -2 down, reduce it by 1. And then again, if you want to get all fancy, you can do it as -2/x to the cubed power, but not necessary. Okay, so let's suppose, before I go on, well, we'll do it here. Let's suppose I have a number in front of that. So if I have x cubed, we already did that, that's 3x squared. What if, for instance, I had 4x cubed? What's the derivative of 4x cubed, huh? Beautiful, 12x squared. You just multiply it by the number in front. Same rule applies. So another way to look at this would be 4 times x cubed. Take the derivative of x cubed and multiply it by 4. Hence the reason it's called the constant multiple rule. You're taking something and multiplying it by a constant. So c is a constant, f is the function, c times f prime. Easy peasy, yes? Good? So that's why 3x squared becomes 6x. And I don't know why I included that in there because there's no constant there. That's a bad example. Let's skip it. Okay, sum and difference rules. I did this already. The derivative of a sum is the sum of the derivatives. The difference of a derivative is the derivative of the differences. No product, no quotient. They have their own special rules, which we'll get to later, and they're nasty. But this is easy stuff. The nice thing about this, and the reason why I included it, even though it's kind of obvious, is that this is what allows us to take the derivative of polynomials by looking at each individual term. So if I have a polynomial, then the derivative of the polynomial is the derivative of each of the individual terms. Okay, we good? Need a second? Okay. 1. All right, let's try it. What's the derivative of that polynomial, Paige? telling her she's got a brain, she can do it. We did x cubed already.
I'm not sure.
JJ.
3x squared minus 4.
3x squared minus 4. Hold on a second. Where did the x go?
What do you mean?
How did negative 4x just become negative 4?
Because the x is the first power. And you subtract it by 1.
Beautiful. Okay, so this seems to create a number of problems. If I want to take the derivative of negative 4x, let's suppose that's my function. There's two ways to think about it. What can you tell me about this function y? It's linear. And as we talked about already, the derivative of a linear function is a slope. What's the slope of negative 4x? Negative 4. Okay, that's one way to think about it. However, what JJ just said is that, if we get rid of this, this is x to the first. Bring the 1 down. 1 times negative 4 is negative 4. Reduce it by 1. What's x to the 0? 1. So we're left with negative 4. Where'd the 5 go? Huh? Derivative of a constant is 0, so we get that. Well done. Luke, what do you got for me, buddy? What's a good one?
Is it?
That's over 2.
Okay.
Yeah, negative x to the 4th over 2.
Oh, okay. Negative 4x to the 3rd over 2 plus 6x squared. Minus 2.
2 quick things. What's negative 4 over 2?
Oh, is that in like its own like? Is it x to the 4th over?
All over 2.
All over 2.
Or if you prefer, negative 1/2 times x to the 4th. Your answer wasn't incorrect. You could just simplify the fraction. But you did make one small mistake. What's 3 times 3?
Oh, it's 9.
No.
I thought it was 2.
No, there you go. Bring the 3 down, reduce it by 1, and we talked about the negative 2 already. I would argue that this is a lot easier than what we did yesterday. So can you imagine having to take the derivative of x to the 8th using yesterday's limit process? In case you can't, I'll show it to you. You would do the limit as delta x approaches 0 of x plus delta x to the 8th power minus x to the 8th all over delta x. And you would have to take x plus delta x to the 8th power somehow. Pascal's triangle maybe? Or just cry. However, with what we just learned, we know that f prime of x is 8x to the 7th. Quite a bit easier. We're going to stop there for today. So we still have to talk about trig. We still have to talk about a number of things, but for now, that will get us where we need to be. So let me stop this. Shut up.